really all I'm saying with that. All right, so we could always verify it in the calculator though. So limit as x approaches 0 sine x over x. Take a look at the picture if you want. So it's a trig function. Which zoom option do you think is most appropriate?
Zoom fit.
7, zoom trig.
Zoom trig, yeah. Yeah, there's a lot of appropriate options. The one that's most appropriate, like if we were in a stat course.
Zoom stat.
Zoom stat, yeah. All right. So there it is. Now I want to see where this graph is going as I approach 0 from the left and from the right. Well, it's going right there. It's a question of what's there. You could trace along and just eyeball it. See, it says 0 comma nothing. Not nothing as in 0, nothing as in nothing. Like there's nothing there, there's a hole. But from the right, it looks like 0.99-ish. From the left, it looks also like 0.99-ish. If we assume it's a whole number, solid bet that it's a 1. All right? If you don't like that, because again, you know, it could be a trick question. Maybe it's not 1. Maybe it is actually 0.997. You know? So you go into your table set. All right? This is your workaround. Anytime you have a limit question and you're just not quite sure algebraically how to do it, put your limiting constant in as your table start and make your delta table super small. All right? Then go into your table, second graph. Center it around your limiting constant and look to see if that error is in between two numbers that are obviously close to one another. All right, in this case, it's between 1 and 1. Safe bet that our answer is 1. All right.
How do you get to that menu again with the table sort? Second what?
Second window.
Oh.
All right. I'm going to go over this skill repeatedly because that's how important it is. You'll never get a limit question wrong.
So for when you go into the table set, what are you trying to find? What do you get on this graph?
You're getting, so the 0 value is your the value that you're approaching. Right? From the top, as you approach 0, that's the same graphically as coming in from the left. Coming in from the bottom is the same as coming in from the right graphically.
Well, what do the ones mean?
The ones are just telling you what the y values are getting closer and closer to. So if you actually follow the progression, because the issue is the ones on this screen are just rounded values, you could see that the y values are really 0.99 something. Getting larger and larger appears to be approaching 1. And then here, the values are getting larger and larger, also appear to be approaching 1. All right? So it's really just showing you the trend for y. What is it getting closer and closer to? All right? So that's a way to handle pretty much all of these problems. But again, it depends on the instructions. These questions, they evaluate the following limits, but on a test it could say analytically. Analytically, again, is the algebra of calculus. All right? What that means is by hand. All right? So what we want to try to do is fit each one of these problems to one of the rules that are given. So number 1 kind of sort of looks like the first rule, you know, with some exceptions. There are some ingredients that, you know, are extraneous. So what I'm going to do is I'm going to use my algebraic skills, because I got lots of them, and so do you. You don't get to this course without having a decent handle on algebra. All right? Most basic form of algebra, if you're dealing with factoring and distributing, greatest common factor. All right. I have a 3 that could be taken out of the top. That is not a marker. I have a 3 that could be taken out of the top, and a 2 that could be taken out of the bottom. So limit as theta approaches 0 of just sine theta over theta. All right. There's a lot of rules associated with limits, but algebraically, the most basic one is if there is a factor that does not have the limiting variable in it, it doesn't need to be in the limit. If there is a factor that does not have the limiting variable in it, then it does not need to be in the limit. So 3/2, those are factors of these expressions, right? 3 times the sine of theta, 2 times just the theta. They don't need to be in there because they don't have thetas in them, all right? Now, if I had even more complicated, but actually it works out nicely, let's say this was x times the sine of theta. X is not a theta. X doesn't need to be in there. It's unrelated to the theta. So it does not need to be in the limit. You can factor it out.
Should I change my calculator to polar mode so I can put thetas in the y area?
You could, but you'll find yourself changing back and forth pretty repeatedly.
So it's just not worth it.
Yeah, at least not yet. All right. So this expression, the limit as theta approaches 0 sine theta over theta, follows the limit as a approaches 0 sine a over a, follows that model, and so that's going to give us a 1. So we're looking at 3/2 times a nice uno. All right. So it's really the same idea as just canceling it out, but as long as you know it's equivalent to 1, you'll know what to do. Yeah. The issue is, and you know, before when I was talking about verifying it on the calculator, the issue is people sometimes get it confused with the cosine rule, which is equal to 0. All right, so you know you just got to be careful. There is an element of studying that comes into play, but at least if you're kind of in the game, then you're going to be in good shape, because part of the challenge is knowing when a rule applies. Sometimes you don't even need to know what the rule is. That once you know that a rule is in play, then you can kind of figure out what needs to go where. But and honestly, thinking back to the calculator, let's say you completely whiffed on this rule. You go in, you take the test, forget the rule completely. You get to this step because you remember you can take a 3/2 out, right? But then you put the original function in your calculator and you see that the limit is supposed to be 3/2. So what must this be equal to? In order for this whole thing to end up being equal to 3/2, like the calculator says, it would have to be equal to 1, because that's just the way it has to work. So you get around knowing the rule. But that's like in case of emergency.
So, like on number 2, you get to just limit cosine theta. Do you just plug in 0 for theta?
Yes. To the point where I'm not 100% sure why that problem is on this page. Because it doesn't involve...
Tangent to sine and cosine.
Yeah, it doesn't involve any of the rules. It's a weird one.
What's cosine theta?
I'll take it as a typo. Yeah. But, yeah, so this one is just general knowledge of trig. Theta approaches 0. Sine theta over sine theta over cosine theta. We have 2 fractions being divided, so a little keep, change, flip action. So we're looking at sine theta multiplied by cosine theta over sine theta. So troublemaker's gone. Theta approaches 0, cosine theta. Notice how I'm writing the limit every single time, as annoying as it is, because the theta has not been substituted in for yet, right? So the theta is still part of the expression, so the limit has to be there. You don't want to lose credit for that. So now I can write cosine of 0 without the limit because I've applied the limit by doing the direct substitution. Cosine of 0 is equal to what? 1.
Wait, how did? Oh wait, let me use.
All right, so let's take a look at number 3. And then after that, I think I could set you free. Because number 3 is actually harder, more trickier, I guess. Yeah.
What mode is the calculator have to be in?
Radian move. Radian move. All right, so number three is one of those iffy kind of questions where if you know properties of trig functions, you can do something with it, but general rule of thumb, it's got cosecants, cotangents. Let's get it in terms of sines and cosines. All right. There's other ways around it, but this is generally going to be your best bet for a consistent approach. All right. So, because I'll tell you, when people get jammed up on this kind of stuff, it's usually in step one. Like once you get past step one, everything usually kind of works out. This is a good step one pretty much all the time when you see a reciprocal function. Pro tip. All right, so once you do that, it should be at a point where like the algebra coalesces in your brain. It's kind of a nice moment, because once you realize that you have a common denominator across the board, that in a complex fraction, what does that mean? Cross them out. Get rid of them. You could do the keep, change, flip action, but yeah, I think it's a wasted step. However, that being said, on a test, it's never a wasted step if it's the step that allows you to get the question right. So, you know, for efficient algebra, I think it's a wasted step. But for the purposes of doing well in a math class, it's never a waste. All right. So then, if you don't know your rules, you might take a look at this and say, I don't know what to do next. But we do know our rules, so we know that this is going to be equal to 0. If I could get a nice video of all the entire page completed, so I'm kind of excited about that. All right, so you look at something like number 4, and at first glance, it doesn't look like it follows any of those rules. So you would say, okay, cool, nice conversation about those rules, but immediately we get to a problem where it falls apart. That's actually not the case, because if you look at it, you can see that there's a theta in the bottom of the fraction. Two of the rules above have thetas in the bottom of the fraction, right? One of the rules has a sine of x. This doesn't have signs anywhere. I mean, I guess I could transform this so that it has a sign, but one of them has a 1 minus cosine of x. So you remember those trig identities that you were working on in pre-calc? You know, get the left side equal to the right side. We reviewed that in the first, or in the review packet. It was really to handle problems like this, so that you could manipulate trig expressions so that you could make it more manageable. That being said, you don't need an identity here. This is the difference of perfect squares. It's factorable. All right? So I'm just going to factor the top. Now, there are some problems that you're going to work on in this part of the packet where you may have the experience of, yeah, that's great, I never would have thought to do that. If you have that experience sometimes, that's okay, because a lot of these questions are to get you to have already experienced these kind of questions before you see it for a second time, like on a test or a quiz. All right, I never would have thought to do that. Well, now you will. All right, so that's the main idea. Anyway, it factors to 1 minus cosine theta, 1 plus cosine theta. On the bottom, I still have that theta multiplied by 1 plus cosine theta. All right, so we have a common factor top and bottom. Wipe them out. Now, one thing I kind of neglected, and it's very easy to gloss over it, one strategy that you can deal with in pretty much any situation, or might consider using in any situation, is direct substitution. Sometimes it just works. All right, so before you actually go down an algebraic path, maybe try plugging in the values, the limiting constant for theta, and see what comes up. It's just in this case, you know, from years of doing the same problems over and over again, it slips my mind because I already know it's going to be 0 over 0, so I know to jump right to the next step. But you know, if you're starting a problem, you're looking at it for the first time, thinking forward to the test, try the direct substitution. Maybe it's just that easy. All right. So clean cancellation, limit as theta approaches 0 of 1 minus cosine theta over theta. All right. The notation is so important, folks. You got to make sure that you don't lose the limit until you perform the substitution. All right. If there's a variable still in the expression, you have to have limit in front of it. All right. Once you replace the variable with a number, then you could drop the limit. All right. Now this is by rule equal to 0. All right. This is, I hate doing it because it makes it seem like I'm trying to be pretentious or fancy.
3? I
Yeah.
don't get it.
That means equal by rule. I just didn't want to write equal by rule. So if you throw a third equal, like a third line to your equal sign, that means by rule. All right. You do not need to know that notation. All right. But if it's something that you think you're going to remember, go for it. All right. What this is telling me by writing that, or telling anybody by me writing that, is that I didn't get this answer by doing substitution or any kind of algebra. I got it because there is a fact somewhere in math world that tells me that this is equal to 0. All right. If you just wrote a regular equal sign, you still get full credit. All right. Sometimes in my attempt to be lazy, I end up making more work for myself. So I think that was an example of it. All right, the next one, number 5. You take a look at that problem and you say, this doesn't look anything like those rules. A key indicator for any one of these questions is the presence of a loose variable. So a variable that's not contained within a trig function. If that's the case, odds are you're dealing with a rule even if it's not obvious from the word go. I'm looking at reciprocal trig functions. Anytime you have reciprocal trig functions, I'm thinking back to pre-calc. The instinct might be to make them into something more familiar. Or at least that's what my instincts tell me. And I encourage your instincts to think the same way as me. Because at least in math, you'll probably be better off for it. So this is equivalent to 1 over cosine theta over theta times 1 over sine theta. All right. You're looking at it and you're still maybe not seeing the rule. All right. So we clean it up. Limit as theta approaches 0, 1 over cosine theta over theta over sine theta. Maybe you're still not seeing the rule. So maybe do a little keep change flip action. Limit as theta approaches 0, 1 over cosine theta times sine theta over theta. All right. So I'm looking at this now and I'm seeing part of it as the rule. All right. The first rule above, the limit as a approaches 0, sine a over a. That's this piece right here. All right. A commonly forgotten rule from pre-calc is that if you have a product, some product, difference quotient, any of the four, really any operation, they all transcend the limit themselves. Fancy way of saying, if I have the limit of a product, I can rewrite it as the product of the two limits. All right, meaning I can rewrite this as the limit as theta approaches 0 of 1 over cosine theta times the limit as theta approaches 0 of sine theta over theta. All right. It's kind of like a violation of algebra rules, but it's a technique that works specifically only for limits. All right. So if I had something like, for example, the sine of x times y, that would not become the sine of x times the sine of y. That's just not how anything else works, but for limits it does. All right, so if I had the limit of this 1 over cosine theta plus sine theta over theta, I could rewrite it as the limit of the first thing plus the limit of the second thing. Right, so if you think about it as kind of like the distributive property, just not just for addition and subtraction, then that's probably a good way to go. All right, so then you get to this step, and if you're not familiar with the rules, you might get jammed up. But this one is equal to 1. And what I find is after a period of time, what people end up doing, after they get to the point where they know all these rules, they're comfortable with the rules, they feel good about them, they start trying to make everything a rule. Limit as theta approaches 0, 1 over cosine of theta. They're looking up at the top of the sheet, looking at formula sheets, trying to find a rule to fit that one. Sometimes it's just direct substitution. Plug the 0 in for cosine, see what you get. 1 over cosine of 0. What is the cosine of 0? 1. So 1 over 1 times 1 is equal to 1. All right, so let's say you didn't know that. You're taking the test, you're terrified that this is going to be the thing that causes you to not meet any of your goals in life. All right, this one problem, you're jammed up. You got to this point, and you even figured out this part. Right? There's no reason why you can't just chuck that in your calculator and get the number. Right? Because ideally, honestly, if you're really on the ball with this stuff, you should be able to do this in your head anyway. So you should be going from this to that without showing the intermediate steps. So if that's the case and I'm letting you use the calculator, what I'm telling you is that all I need is that number. You write the number down, I look at it and say, wow, great job, you did it in your head. And you walk away and say, yeah, that's cool, I did it in my calculator. The bottom line is it looks the same to me, so who cares, all right? So work towards being able to do stuff like that in your head, but settle for doing it in your calculator when push comes to shove, all right? Bottom line is, on the test, you should have the ability to come up with every single limit answer. The question is, can you get the algebra to work out sufficiently to justify that answer? All right, so you know how to get the answers, so you have an answer key, a mobile answer key on the test. So there's no reason you should get things completely wrong. It's just a question of justifying it.
Is this an independent test on Friday?
Unfortunately,
okay.
Yes. It's kind of the thing, I mean, don't hold me to this, but it's going to be like in every other assessment, generally the big ones. So group, individual, so until we stop with the individuals.
Stuff, or like just this limit and continuity stuff, or is it this whole packet?
Whole packet is limit and continuity, so it's that. Yeah, tomorrow's actually going to be the last day of new material. It's all practice after that. So we got a lot of time to work on this stuff. So the last one that I wanted to go over, and this is the one that can be a little mind-bending for people, but I kind of already went over it in the calculator, just I didn't show you how to do it by hand. So this one's really important because it can be very frustrating when the calculator tells you what the answer is supposed to be, and you just can't get the algebra to work itself out. All right? The rule tells us, and I'll just write it down here so I don't have to go back and forth. The rule is that the limit as a approaches 0 of the sine of a over a is equal to 1. All right? The important characteristic of that rule is that these two values have to be the same. That looks like I just erased it. That sucks. These two have to be the same. These two are not the same. I want to make them the same. So what I can do is introduce a 5. I'm just going to pop it in right there, just for the heck of it. I'm just going to throw a 5 in the bottom of a fraction. Is that a legal move? No. Absolutely not. I multiplied the bottom of a fraction by a number. If I had 1/2 and I multiplied the bottom by 2, now it's 1/4, it's not the same value. It would be the same value if I multiply the top by that same number, right? So let's do that. So now it fits the rule, or at least the main part of it, sine 5t over 5t, that fits my rule. I got that extra 5 there. The good thing about limits is that anything that you think that you might want to do instinctively, algebraically, is probably going to be a legitimate move, even if it's something that doesn't, like feel like it would work in other algebraic senses. It works for limits, all right? And the important thing to remember, or one important thing, is that the limiting constant t is approaching 0. The t is the important variable. So that's the only thing that actually needs to remain within the limit. Anything else can be factored out. So that 5 does not need to be in the limit anymore. So all of that was just me saying we can take the 5 out. But the reason I bring that up is because let's say instead of it being 5 times the sine of 5t, let's say it was x times the sine of 5t. That x can be pulled out of the limit because it's not a t. If it doesn't involve a t, it doesn't need to be there.
So you put it in front of the limit?
Put it in front of the limit as a constant multiple, or kind of like a greatest common factor. All right? So then by rule, or even by your calculator, this is a 1, and this is a 5. So 5 times 1 is 5. And again, just like the last one, let's say you get to this step. You got the 5 outside, and you have no idea what this is going to end up being. But you put the original problem in your calculator, and you already know that the answer is supposed to be 5. You have 5 times this whole limit thing, and you know it's supposed to be equal to 5. Logically, that means that this has to be equal to 1. Right? So even if you don't know the rule, you can kind of invent the rule on the fly. All right? This test on Friday is not a test that should be scary. All right? When I'm showing you these calculator techniques, if you really take them seriously and try to actually use them, they're lifesavers. Like, you get jammed up on a problem, the calculator gets you out of the jam. All right? So I promise you. And we'll debrief after we take the test on Monday next week. I'll ask you if I was telling the truth or if I was full. All right? And I think most of you, if not all of you, will at least be able to point to a moment during the test where the calculator saved you. All right? So please take it seriously. And if you have questions on how to use it properly, let me know. All right? Because some of them are a little, some of the techniques are a little out there. All right?